the verification of uninterpreted program is undecidable in general. You can get decidability by restricting the programs you consider.
Okay, hello, I am Umang, and I'm a PhD student at Illinois. And I'm going to be talking about uninterpreted programs and their verification and the decidability result we have in this context. So this work, part of this work appeared at Poeple 2019, and it's a collaboration with a lot of people, including professors and other students at Illinois. So without further delay, let me directly jump into the problem. Okay, so let me make a rather obvious statement here. Program verification is undecidable in general, and while we do know of existing decidable classes, most of them are either those that are meant to work on finite domains, so essentially Boolean programs, or things like Petri nets. So Petri nets can have counters, you can increment them, you can decrement them, but you cannot really test for 0. And that means they're not a natural class for programs. So in general, when you talk about verification without any loop invariance, this problem is undecidable when programs are meant to work on infinite domains. And therefore, it requires a lot of manual effort to verify these programs. So manual effort including loop invariance or contract. So this talk is about uninterpreted programs. And let me give a brief summary of what these are. So these are programs, just like any other programs, sequential programs. They have constants and functions and predicates in their vocabulary, but these symbols are completely uninterpreted, and I will come to that in a moment. These interpretations are data models. So these programs are meant to work over arbitrary data models. So data models are like first-order structures, and these structures come with their own interpretations for these symbols. And now the verification question is essentially, is it the case that over all these data models, some postcondition holds true? Okay, so here is an example. It's a straight line program for the sake of simplicity. So you assign x2 to x1, then you assign y2 to y1, and then you compute z1 to be f of x1 y1 and z2 to be f of x2 y2. And at the end, you want to assert whether z1 is equal to z2. So in order to reason the correctness of this program, what you really need to understand is that a simple reasoning about equalities is enough, and you don't need some more complicated properties about the functions. So these functions can be arbitrary, and still the postcondition holds. So that is why it's an uninterpreted program. So let me talk about the contributions of the Poeple paper here. The verification question for these kind of programs is undecidable, not surprisingly. But then in the paper, we also show that there is a class of programs called coherent, and more generally, k-coherent programs that admit decidable verification. And this is the main result of the paper. So to the best of our knowledge, it is the first class of programs that are meant to work on infinite data domains and yet admit decidable verification. We show that even with recursive function calls, there is decidability. So without any recursive function calls, the decision procedure is a p-space decision procedure. And when you have recursive function calls, you have x-prime decision procedure. We show that when you relax this notion of coherence, you immediately land up in undecidable territory. So these are the main contributions of the Poeple 19 paper. Let's go back to uninterpreted programs. These are like any other sequential programs. You have assignments. So x is assigned y. You have x is assigned f of z1 through zk. So this f here is uninterpreted function. And then you can have conditionals. You can have loops, etc. So conditionals here are Boolean combinations of equality atoms. So variable x is equal to variable y. or predicates like R is a relation, R of Z1 through Zk. So R again is an uninterpreted relation here. And you can write postconditions again as Boolean combinations of equality or uninterpreted predicates. So the verification question for these programs more formally is the following. So if you have an uninterpreted program P, and if you have a postcondition phi, the verification question asks if it is the case that for every data model M, so recall that a data model gives you the interpretations of all the functions and relations and constants in your program. So is it the case that for every data model M, and for every execution row of this program, such that that execution is feasible in the data model, is it the case that the postcondition holds at the end of the execution? That's the verification question. So let's look at this example. So this is an example of list search. So you have a list, and this program basically searches for a key k in a list segment that starts at x and ends at y. So it starts b to be false, and then inside the loop, it checks whether the key of the x variable currently is equal to k, the key that you're looking for. And then if it is so, then it reassigns b to be true, and the return value r to be x. And then if that's not the case, then it goes on incrementing the pointer. So x is assigned next of x. And the postcondition says, if whenever b is true, it is the case that the key of r is equal to k. So you can think of this program as an uninterpreted program. That means you can work with any interpretation of the function next or any interpretation of the function k, key. So the verification question in this context then becomes, check if for all interpretations of the function key and the function next or n, and for all initial values of the variables x, y, b, r, k, is it the case that the formula b equal to t implies key of r equal to k holds at the end of every execution? It turns out that this is a coherent program, and this is the class of programs that we can verify. So this program can be verified without any loop invariance. So we know that in general, undecidable programs cannot be verified. It's an undecidable problem. But this class of programs called coherent programs is something that admits decidability. And let me before we delve into the definition, let's look at this algebraic view of program executions, and that will help us understand the definition. So executions of uninterpreted programs are essentially sequences of statements. So you can have assignment statements, so x is assigned y, or x is assigned f of z1 through zk. And you can have these assumes, so assume x equal to y, or assume x not equal to y. We can, for the sake of convenience, we can just skip the relational predicates. They can be model-less functions. So these are the kind of statements in your executions. And with every execution, you can associate algebraic view. So that algebraic view tells us what are the terms that are computed in the program, in the execution, and what are the constraints, or what are the assumptions that are accumulated over these terms as the execution proceeds. So let's look at an example to understand this algebraic view. The same example on the left. So you have the variables y, k, x, t, t, f, b. And initially, each of these variables are associated with the uninterpreted term. So y is associated with the term y0, which is a constant term. Similarly, k is associated with k0, etc. Now, if you look at the first, now let's execute the program, and let's accumulate terms and constraints. So the first constraint that we get is t not equal to f. The term corresponding to t at this point is t0, and the term corresponding to f at this point is f0. So you get the constraint t0 not equal to f0. As you proceed, you get b is assigned f. That means that the term associated with b is now f0. And now you enter the loop, and once you do that, you accumulate the constraint x0 not equal to y0. Now the next statement is the computation of a term. So you compute the term key of x0, because the term stored at x at this point is x0. So you get a new term x0, and now you say that the variable d points to this term. And then so the constraint that you accumulate is key of x0, which is the term d, is not equal to k0. And then like this, you can continue, you can compute more and more terms and accumulate more and more constraints. So let's say at the end, we enter this conditional, and the corresponding constraint is key of n of x0 is equal to k0. So that's the algebraic view. You compute terms and you accumulate constraints over these terms. Okay, so with this, let's look at the definition of coherence. So coherence is a property of execution. So recall that executions are sequences of statements, assignment statements, term computation statements, and assumption statements. And this definition is intrinsically tied to the algebraic view of such executions. So an execution is coherent if it satisfies two properties, memoizing and early assumes. And let's look at both of these properties in detail now. Roughly, memoizing says, don't recompute terms. Or in other words, if you recompute a term, then that term is already present as part of some other variable currently. And the next condition, called early assume, says that, well, assumptions are early. It means that whenever you make equality assumptions over terms, then you do not have any super term of the terms that you make equality about, that you assume equality about. Let's look at the formal definition of memoizing. It says the following. If you have a prefix of an execution of this form, sigma followed by this assignment x is assigned f of y, and let's say the term f of y is t, then, and let's say it was computed earlier in sigma, then it must be the case that there is some other variable z which holds the same value at the end of sigma. Now, you can have equality assumptions, so you have to relax this definition and account for equivalences of terms. So in general, it is the following. If the term t has been computed before modulo equivalences, then there is some variable that contains the same term modulo equivalences. Okay, so let's go back to the same example. Here, the different terms that are computed are the following. There is x0, then there is n of x0, there is n of x0, etc. And then key of x0, key of n of x0, key of n of x0, etc. Now, each of these terms are computed only once. So there is, by definition, no recomputation. So this is vacuously a memoizing program because all its executions are memoizing. Let's look at the second constraint, early assumes. It says the following. If you have an execution, if you have a prefix of the execution of the form sigma followed by an assume of equality, x equal to y, then let's say there is a term s, which is a super term of the term stored in x or y. And if that term has been computed by the execution so far, then it must be the case that this term s is already present in some variable again. So in short, if you see an equality assume, it must be early enough. It must be early enough so that no super terms are computed. Okay, so a program is said to be coherent if all its executions are coherent, meaning they satisfy the two requirements, memoizing and early assumes. Now, we show that for this class of programs, verification is decidable. That is, for programs without recursion, you get piece-space completeness. And for when you have recursion, you have X-time completeness. So notice that this is the same complexity class as that of Boolean programs. And again, I would like to emphasize that this is the first class of programs that work over infinite data domains, because we consider all data models and yet admit decidable verification. And we show that when you relax either the memoizing condition or the early assumes condition, the problem becomes undecidable. So these are this is a tight characterization. Let's look at the decision procedure and the key ideas in the decision procedure. It's called streaming congruence closure. So this is an automata theoretic procedure. It analyzes executions in a constant memory fashion. So yeah. So the idea is to maintain congruence of terms. If you look at this example, again, as we said, the only reasoning we need here to assert the postcondition is that when x1 and x2 are equal, and when y1 and y2 are equal, then it must be the case that f of x1, y1 is the same as f of x2, y2. This is the congruence axiom, and that's what we need to argue correctness. And essentially, that's what our algorithm does. Now, it so happens that in general that may not be possible, but the restrictions of coherence make it possible. So this is an automata theoretic procedure, and the states of the automaton essentially maintain these three things, tilde, D, and P. Tilde is essentially equivalences between the variables, meaning what variable is equivalent to what variable. D maintains what variables are disequal from from the other variables, and the last component tells you the functional relationships. So it tells you whether the variable B is equal to f of the variable A, etc. So this is the kind of decision procedure this algorithm is. And now one can show that the set of executions of a program is a regular language, and so is the set of executions that are coherent and correct. And therefore, the verification question boils down to intersection of two languages. Since both these languages are regular, we get a decidable algorithm. Even when you have recursive function calls, both these languages are visibly push-down languages. So again, we have decidability here. In the paper, we also show that a similar algorithm can be used to check if if an uninterpreted program is coherent. So that is also decidable problem. Let's look at this next set of results that we have. So consider this program on the left. It essentially iterates over a list. So x and y are pointers in the list. They are maintained so that they're separated by a node in between, and they both move together on the list. Now, if you look at this program, it so happens that you are recomputing a term. So there is y, which is n of x, and then there is and here it is n of x again. So you are recomputing it, but then you had dropped it in the middle. That means you're essentially breaking the memoizing restriction. But then it so happens that you can add some more variables to this program and then make it coherent again. So I can add this ghost variable g and make sure that I'm not dropping the intermediate values. So because we could add just one variable and make it coherent, the original program is called one-coherent. So that's the next set of results in the paper. We say that a program is k-coherent if it can be made coherent by adding k new variables, and assignment to these variables. So again, checking if a program is k-coherent for a fixed k is decidable in p-space, and further verification of these programs is p-space complete. So far, we have looked at verification of completely uninterpreted programs, meaning you don't need any other reasoning besides the fact that they follow congruence axioms. But sometimes it may not be possible to prove correctness just based on this reasoning. So that's why we try to extend these set of results, include constraints on the functions and other symbols. So let's look at this example. This example tries to search for the minimum of 3 elements A, B, C. So it says if A is less than or equal to B, and if A is less than or equal to C, then assign A, otherwise assignment C. And in the second branch, it says if A is less than C, condition that the min is less than or equal to A, and is less than B, and it is less than C. Now, this postcondition may not hold on all data models. And let's look at an example why that could be the case. So if less than is completely uninterpreted, this is one model in which this program may not be correct. So here we have 3 elements, A0, B0, C0, and A points to A0, B points to B0, C points to C0. And the relation is interpreted as follows, as a cyclic relation. A0 is less than B0, B0 is less than C0, and C0 is less than A0. So it's a cycle. So it's not a total order. So that means not all models will satisfy this postcondition. So, but when less than equal to is interpreted to be a total order, meaning it satisfies these 3 axioms, reflexivity, symmetry, and transitivity, then on all the models in which less than is interpreted as a total order, this program will be correct, meaning the postcondition will be satisfied. So that's the bottom line. In general, programs may not be proved correct when symbols are completely uninterpreted, and you do need certain assumptions on these functions and relations to prove correctness. And that gives rise to this question of verification modular axioms. And this is the corresponding question. So now we have the program P, a postcondition phi, and also a set of axioms that constrain your function symbols and relation symbols. And now you want to ask is it the case that for all models that also satisfy the axioms, is it the case that the postcondition is true at the end of every execution? This is what the verification question becomes. So with this question, we try to investigate decidability for several classes of axioms. In general, if you have a lot of power in your axioms, you will get undecidability. So the first class of results, we consider axioms that constrain your relations. So in general, you can write an EPR formula. So EPR is a class that says exists X for all Y and then some formula. So this class, if you restrict your relations like this, then you get undecidability. But for all other usual classes of relations borrowed from practical applications like reflexivity, symmetry, total orders, we show that we do admit decidability, this class of programs. Similarly, we try to investigate what happens when you try to constrain your functions. So when your functions are associative, you immediately get undecidability. But for commutative and idempotent functions, you get decidability. And we also show that if you look at any subset of the decidable axioms, any combinations of those will also be decidable. So far I've talked about coherent programs and k-coherent programs and showed that these admit decidable verification. It is indeed the first natural class of programs that work over infinite domains and yet admit decidability. The decision procedures are fairly efficient, as efficient as that of Boolean programs. And I also talked about extensions to theories, so axioms. Since then, we have also extended it to other results. So we investigated how we can add support for deep manipulating programs. So for these programs, we need to reason about updatable maps. So you can update your functions as next of X is assigned to Y. Now that is something that is that's not supported in uninterpreted programs. So we investigated how we can provide support for these programs. We also since did this result to the following result, that if you want to synthesize coherent programs in a grammar-based synthesis, SIGUS, then it so happens that this is a decidable problem again. And this was a talk by Paul in the morning. So that's all. Since we've been very excited about this set of results, and it takes a fresh look at verification and synthesis. And we do have a lot of exciting avenues to follow. And yeah, that's all. So to conclude, I'm looking for faculty jobs and also jobs in industry research. So I'll be happy to talk to any potential people.
Any questions? Okay, I'll start with one then, if there is no questions. So how restrictive in practice are the class of functions that you're giving?
So the class of programs,
say the first class.
The coherent.
Yeah, the
programs.
coherent one.
Yes.
How restrictive is it in practice?
So one can intuitively think of them as programs that work in a one-pass way. So for example, if you had a list and you were iterating over that list in 2 passes, then that would naturally be incoherent because you would be recomputing terms, and if the list is unbounded, you will not store all of the terms. So that's not a coherent program. So in general, if you have streaming sort of programs which are one pass, that would be the class of programs that falls into this class.
Boy, I mean, this is a related question, but I guess maybe asking for more like concrete examples of the kind of concrete examples of actual programs that would fit into this class, and then what could you prove about them? So like.
Yes, so we do have, so this heap manipulating programs, we in fact have a tool that also decides. So, these are, so we did look at programs like finding an element in a list, or deleting an element in a list, or essentially list programs or tree programs. Those are the classes of programs that can fall into this. For that, yes, you can do it as long as, so finding a min essentially requires you to reason with orders. It turns out that orders are also decidable. So yes, that also works.
Hi. So you mentioned that the conjunction, so you mentioned that interpreted programs when conjunction with EPR is undecidable, right?
Yes.
That's a bit significant because the EPR essentially can ground. They're effectively propositional, right? So you can ground them to basically propositional formulas. So does
That's
that
right. Yes, it was a surprise to us also. Yes.
does that mean that any propositional formula in conjunction with interpreted programs is undecidable?
It's not quantified, but because EPR is the quantification, that. So you can also quantify relations. That's the
Yes.
arbitrary quantification of a relations ends up being undecidable.
Okay.
Okay, okay. Are coherent programs related in some way to streaming string transducers or streaming
So we did
transducers
come
in
across
general?
those. In streaming string transducers, it's not clear if you can reason about congruence, meaning data. So if I have x, and if I apply a function to f of x, and if I have something that is equal to x, and then I apply the same function, it's not clear if you can argue that the resulting things are the same. So that's the limitation of transducers. You can increment, let's say, a list, every element of a list by 1. And then if you want to, let's say, argue that the new list is also sorted, then that would be something that would be hard to argue with just transducers.
Anything else? Okay. One more.
Is there any sort of intuition for why something like associativity all of a sudden makes it undecidable, or is it just like?
So
certain
it was a
things-
surprise to us again. In fact, so the other two functional axioms like like commutative and idempotence work using a similar technique. So we were hoping that the same technique would work, but it doesn't. In fact, for a long time we thought so. And the reason is that for commutativity, for associativity, so the associativity axiom that I'm talking about is f of xy comma z is f of x comma fyz. And now you have to reason about terms that are not currently present in your window. So that reasoning is hard.
Okay, thank you. Let's thank the speaker again. Shankan Lin from